Okay, let's start. Greetings. This is the first lecture of literature and history of math science, organized jointly by CMSA in Harvard and YMSC in Tsinghua University. And this is supposed to be second talk. The first talk was canceled because of the illness of the speaker. So anyway, Mark Kisson will be the chairman of this talk today. So Mark.
Thank you, Yao. So it's a pleasure to introduce Don Zagier from the Max Planck Institute in Bonn and also the International Center for Theoretical Physics in Trieste, Italy. Professor Zagier is a member of the National Academy of Sciences. He's won the Cole Prize and the von Staudt Prize, and he will speak on quantum topology and new types of modularity.
So, thank you very much. I hope you can hear me, and I hope when I write you can read it, and that if you can't, somebody screams virtually and lets me know. So this is, I've understood, a very prestigious series, so I'm very happy to be speaking. I don't quite understand what a mathematical sciences literature talk is, as opposed to simply a math talk. Of course, there's lots and lots of literature on quantum invariance and topology, and I hope there will be more very soon, because the papers I'm talking about now, it's a whole series, mostly with Garoufalidis, and they should be coming out, well, two, I hope, in the next 2 weeks. So I want to tell a story that is very close to my heart, because like many mathematicians, what I love most in mathematics is when, sorry? Is somebody saying something?
I don't know where that's coming from.
Aha. Well, I'll continue. If you can hear me, I'll assume I'm still audible and will continue. I was saying that like many mathematicians, what I get particularly excited about is when different fields of mathematics interact, especially in a way that one wouldn't have expected. And the theory of knots is exactly one such field. So everybody knows what a knot is. I'll be talking about knots in general, hyperbolic knots, but I'll have three specific ones that I keep using as examples. So since I'm very bad at drawing, I drew them in advance. Hopefully you can see them. You don't have to know what the knots are. All you have to know is they're called knot number 1, knot number 2, knot number 3, K1, K2, K3. My examples will always be from them. So a knot is a curve in 3 space, which but it's just up to topology. You can deform it and it's the same knot. So there seems to be no connection with other fields like analysis, number theory, algebra, differential geometry, because it's completely flabby. But in fact, the great discovery of, I guess, the 70s of Thurston, essentially, was that that's not true at all, that the vast majority, actually, of all 3 manifolds, but in particular of knots, are what are called hyperbolic manifolds or hyperbolic knots. And that means that the 3 manifold, what you see here is a 1 manifold, but what we care about is the complement. It's the 3 sphere minus the knot. And that thing has a unique so-called hyperbolic structure with constant negative curvature -1. And it's completely unique. So if I draw this thing and somebody else draws a knot that is topologically the same, and we each find a hyperbolic structure, the 2 manifolds will be rigidly equal. They will be metrically equal, so that, for instance, they will have the same volume. So one of the invariants of a knot, very surprising, so that's the first connection, if you wish, between fields, is that knots are in principle part only of topology because it's up to continuous deformation. But the first link is that it goes straight into differential geometry, because if you have a knot, then the 3 manifold associated to it, which is the complement of the knot, the 3 sphere, in the knots I'm talking about, which is the vast majority, they're hyperbolic. This is a hyperbolic structure. And that's a completely unique structure. And in particular, the volume of this manifold, which I'll just call VK, is some real number. And actually, I'll actually use the complexified volume with the so-called Chern-Simons as the imaginary part, so it's actually a complex number. And just to make the numbers specific, I made a little table that now I can't find. well, no, I'll write the volumes later. So the first connection is that knots lead to differential geometry, to a metric and to metric properties. But kind of a corollary of that, because this metric structure is unique, there's a rigidity, the famous rigidity of three manifolds. And that means that everything, in some sense, is defined over a number field. So suddenly, we come to number theory and also related fields like algebraic K-theory that I won't talk about today. And also there'll be the links with analysis, but somewhat unusual analysis, including Q-series, combinatorial analysis, and complex analysis. So that's the next surprise, that to each knot, there's actually a number field in the background. So before explaining that at all, let me just give the data for my three knots. So to each knot, K has a rank. Oh, that's what we call it. By the way, as I mentioned the name, but I haven't written it down. I was going to later anyway, but essentially everything I talk about today is joint work with Stavros Garoufalidis, and in two main papers that are now very near completion. So I don't know if this word is standard. The rank R will be the cardinality of a set that I may or may not talk about again. These are the boundary connections, they're called, or flat parabolic connections. They have two names. You don't really have to know what they are. Basically, these are representations in 2x2 matrices of the fundamental group of the manifold. So if you take the fundamental group of the knot complement, then you look at representations of this into, let's say, GL2C, two-dimensional representations up to some equivalence with some property. But in particular, there are two kind of obvious ones, and I'll number them. So I'll also have a larger set, PK plus. So actually, PK plus is the flat connections, and this will be PK, the trivial one. So we have the flat connection, I'll number them. So J equals 0 will be the trivial connection. So it's the trivial representation. And then another one, which I'll number J equals 1, is called the geometric one. And that's simply that, remember, my manifold was hyperbolic, and that means I can write it as hyperbolic 3 space divided by its fundamental group. And this is then seen as a subgroup of actually SL2C. So that's just the identity representation gives the so-called volume one. And then there's the anti-volume one, which I'll number 2. This is anti-geometric. So there are always at least 3, but usually there are many more. So if I make a little table, if I go back to my 3 standard knots, here's the knot, and here's the rank. So for the figure 8 knot, the rank is 2. So there's the trivial connection, the geometric, and the anti-connection, no others. For the next knot, which was the so-called 5-2 knot, there are 3. And for the 2-3-7 pretzel, there are 6. But this is not just a number. It actually corresponds to the dimension of a field. So to K, we also associate a number field, which is called the trace field. Each embedding of this trace field into C will give one of these connections. And so here, if I take the trace field, Fk, here it's the field Q squared of -3. And here, it's the field, I'll put it in a second, Q of psi. For number theorists, it's a very famous field. It's the cubic field of the smallest discriminant in absolute value, this discriminant -23. So psi is the solution of the polynomial equation psi cubed minus psi squared plus 1 is 0. So that's a very famous field. And strangely enough, it's actually not a coincidence. That's the way you chose these two to study a certain phenomenon that I won't talk about today. The trace field for the last knot happens to be the same. So this cubic field occurs here and here. So you see, this is very strange, because here we have a quadratic field, here cubic, but here it's too small. And the reason is there's actually an algebra, AK, which has a piece, its total dimension will be R plus 1. It will have the piece Q, and then with the piece fk, and then there may be further number fields, which, so I'll just put the dot, dot, dot here, the extra ones. Here there's nothing. We've used up 2 equals 2, 3 equals 3, but here we have a second field, which is again a cubic field. 6 is 3 plus 3, and Q of 8 is the second most famous quadratic cubic field. It's the field, the cubic field discriminant 49, which is the smallest positive discriminant. This is the biggest negative discriminant. And so here there's some equation, but the easiest way to remember it is that the roots, this is an abelian field, and the roots are 2 pi, well, for instance, 2 pi cosine of 2 pi over 7. But if you take 2 pi n over 7, you get the conjugates. So already, I haven't explained in detail how this goes, but you see that from nothing, I draw a picture just on the board, a sloppy picture, a flabby picture, nothing rigid, and then suddenly the 237 knot, which I couldn't draw, gives me, as well as Q, 2 further number fields, 2 cubic fields. Altogether, we have a 7-dimensional algebra. So there's interesting number theory going on. Okay, now my title involves quantum invariance, and basically, I want to start with one invariant that's extremely important and very well known. And then the story that I'm telling, we found that starting from that, by analyzing its properties, there are asymptotic formulas and identities and differences. And it forces you, just by studying the numerical properties of this invariant, called the Kashaith invariant, you find a new invariant. And then if you do it again from those, you find some more, and then you find some more. And it looks like it will proliferate and never stop. But after a while, it's a finite list. And so so the starting point for today's story is a particular quantum invariant called the Kashaith invariant. So the Kashaith invariant, I won't give the complete definition, I'll just give a formula for 1 or 2 of my notes. It's an algebraic number, k is the knot, and for each positive integer, 1, 2, 3, you have this thing, and it can be defined in several ways, for instance, using the nth Jones polynomial, but I'm not going to give the definition. But it's a computable number. I'll give a formula as an example in a minute for the simplest knot, for the figure 8 knot. So this is a collection of, but you see it's in Q bar. So you have certain algebraic numbers. Well, just to make it a little more explicit before giving a dimension, so if I put the 4, 1 knot, which remembers K1, it's the figure 8, then here's a little table. 1, 2, 3, 4, 5, 6. So the numbers are 1, 5, 13, 27, 89. But remember, I didn't say they're rational numbers, they're algebraic numbers. The next one is 46 plus 2 times the square root of 5. In general, they're complicated algebraic numbers. And when you get to 300, it's roughly 10 to the 45. So they grow very quickly, but they're algebraic numbers with interesting number theoretical properties that I'll come to. That will be the starting point. And the ending point will be 3 new, we think they're new, 3 invariants, but actually it's 3 times r plus 1 squared, because each one is a matrix of size r plus 1 by r plus 1. So for my most complicated example, you have a 7 by 7 matrix, that's 49 invariants, and we'll have three different types. They're somehow realizations of the same thing, but it's 3 different invariants. So we get a whole matrix of invariants. And in this matrix, which will be labeled by the 0, 1, remember 0 was the flat connection, 1 was the geometric one, the Kashaev one will be in this position. The first column of the matrix will be very stupid. It'll just be a 1 and a bunch of zeros. This part is interesting, and the top row is interesting, so it's like an extension. And this first number in the top row, this will be the Kashaev invariant. So what I'm talking about is a generalization, but the point is not to find new knot invariants. In fact, you can prove that these invariants will never distinguish knots that the Jones polynomials don't already distinguish. But it's to find new number theoretical properties, and the whole thing hangs together, as I said, just from the Kashaev invariant. You find that this whole story is kind of forced on you, and it is some amazing properties. So that's where I'm going. So I have the Kashaev invariant, which, as I said, is given by an explicit formula. maybe I'll keep one board and say always for the 4-1 knot, how things look. So Kn, in this case, looks like the following. It's 1 plus 4 times sine squared of pi over n, multiplied by 1 plus 4 sine squared of 2 pi over n, multiplied by 1 plus 4 sine squared of 3 pi over n. Well, I'm running out of space, but you can imagine I keep going. So it's an infinite sum, a nested product, but because you have 2 pi times k over n, eventually k equals n, and then the sign is 0, and then everything after that is 0. So this stops. And of course, for 2 sine pi n is an algebraic integer, so this is an algebraic integer, in particular an algebraic number. So that's the Kashaith invariant, and I gave a little table. You see it's algebraic, and it, as I told you, it grows very quickly, and that will be the starting point for the whole story. But first, let me say a little more about the number theory. We're going to generalize this to a function from Q to Q bar. So J is JK, but I'll usually omit the knot. I mean, the knot is always, I have a particular knot in my mind. I won't keep cluttering the notation with the knot. So the Kashaith invariant of the knot is simply the value of this function. Well, I should say it's actually Q modulo Z. So this function is periodic. So you can think of it rational numbers between 0 and 1. And so the simplest numbers between 0 and 1 are the reciprocals of integers. That's the Kashaith invariant. Actually, in general, there'd be a minus, but here it doesn't matter. So that will be the Kashaith invariant. And so here I can say what it will be. J of alpha will be given by exactly the same formula. Now I have to think how it works. It's pi alpha times 1 plus 4 sine squared of 2 pi alpha times 1 plus, et cetera, exactly the same thing. And so if you're a number theorist, you see immediately that these numbers are all not just algebraic numbers, but they're conjugates to each other. And that's generally true. Every rational number alpha, you see this only depends on sine squared, so it's indeed periodic. Every rational number alpha has a denominator n, and then alpha, each the 2 pi I alpha is a primitive nth root of unity. It's conjugate to the standard one. And so this number is a Galois conjugate of that. So for instance, for the 4-1 knot, in the table that is on the other board, this happens to be even for this particular knot because it's a mirror image, an amphichiral knot. I already wrote in my table that if alpha was plus or minus a fifth, you got 46 plus 2 squared of 5. But if you take the other numbers with the denominator 5, so plus or minus 2/5, then you'll get 46 minus 2 squared of 5. So you see already number theory is coming in a serious way. We start just with this strange picture. It doesn't seem to have any number theory. But this picture knows, first of all, that the trace field that I haven't defined is q squared of minus 3. And secondly, there are infinitely many new invariants, each of which is an algebraic number in some cyclotomic field. So we're getting already an interesting function. So as I said, what I'm going to end up doing is to generalize in several different ways, but not by just sitting down and thinking what is a generalization. By studying the properties of these functions, the other functions will show up more or less by themselves. So let me start with the real starting point for the investigation, for this particular investigation. This is a numerical discovery I made about 10 years ago called quantum modular forms, or quantum modularity of the Kashaith invariant. So the first point is before that was the famous volume conjecture of Kashaev, which is still unproved except for maybe 10 knots. So it's largely unproved. Remember that we had this volume. So V, which is Vk, is the volume of the knot. Actually, it's the complexified volume and divided by 2 pi, but let's not worry. So the volume conjecture says that the Kashaith invariant grows exponentially with n, and the coefficient, the exponential factor, is the volume. So that's been open for 25 or 30 years. It's one of the key statements in the whole field, and this directly links the two fields that I had on the board before, the differential geometry, the volume, and the number theory, because this thing is an algebraic number with a certain growth. But in fact, you can be much more precise. In general, it's only a conjecture, but for the 4-not, 1-not, if k is k1, which is the one I was doing as an example, one can be very precise. Namely, this thing looks, it grows like, as I said, e to the vn, but it's not times a constant, there's a power of n. So it's n to the 3/2. Then there's a constant. This was found by Anderson and Hansen many years ago. But in fact, there's an entire power series expansion, which several people, including both Stavros and I, but also other people, I think, found. So there's an expansion which has the exponential factor predicted by the volume conjecture. Now some real number theory comes in, the 4th root of 3 in general, it's something like the square root of more or less the discriminant of the field. There's always an n to the 3/2. But then experimentally, and here provably, there's always a power series. So in general, but it's a conjecture in general, as I said, even the volume conjecture is a conjecture, that this thing is asymptotically equal to the volume of the knot times n to the 3/2 times a power series, 2 pi I over n, and this power series has algebraic coefficients. But if you look here, the coefficients are in q squared of -3, which, if you remember, was the trace field of this knot. Actually, it's a power series with algebraic coefficients, not integers, in this particular number field. All of this is conjectural, but now you really see number theory coming in, and in particular you see numbers, and of course these numbers themselves are interesting knot invariants that are very subtle. It's the coefficient of h squared in this power series, which comes only from the asymptotics. So that's not yet a modularity statement, that's just an asymptotic statement of the Kashaith invariant. But now, I think we don't need this picture for anything. It was just for fun to actually see the knots. That doesn't work, of course. This is Germany. You can only erase things in a clean way. So what I found experimentally, this tells you, this formula, remember Kn was the invariant evaluated at 1 over n. So if I think of the interval from 0 to 1, it's periodic, I'm looking at points approaching 0. So I looked what happens if you approach, for instance, 1/2 and other points. And after a while, I found that's the wrong question. You shouldn't take alpha plus n. So I shouldn't take a over c plus, for instance, 1 over n. Instead, I should take my rational number. So I'll write my rational number always as a over c with a and c co-prime, let's say c positive. And then I extend that to a 2x2 matrix, determinant 1 and integer coefficients. So it's been known since Euclid that if a and c are co-prime, then there are 2 other integers, b and d, such that ad minus bc equals 1. And then it turns out what you should do is not look at alpha plus 1 over n, but instead you should look at gamma of n. So I'm going to look instead at this new function, which remember was defined from the Kashaith invariant by Galois invariants in general. So I take j of an plus b over cn plus d. And now what you find is very beautiful. The n to the 3/2 becomes cn plus d to the 3/2. Before c was 1 and d was 0, so that was the same. The volume term is essentially the same, but instead of n, it's n plus d over c. And then again, there's a power series, but instead of 2 pi I over n, it's 2 pi I over cn plus d. That's experimental. So everything, essentially everything I write is conjectural, but almost always proved for the 4-1 knot, but conjectural in general. So, however, so there's still a power series, but it's no longer 1, 11, 9, 6, 97 over 2. If you do it for the 4-1 knot, at the point 1/2, you get something very similar, but the 11 becomes 41. So it's a different power series, and this depends on alpha, which is the number that I'm approaching. So as you approach a rational number, we get a power series emerging all by itself. Now that's already a beautiful statement, but it doesn't yet look like modularity. In the title of the talk and of this conjecture, which is now in the shadow, I've spoken of modularity. So the full discovery, again, completely experimental, is this. Remember that J is periodic. So J of n is the same as J of 0, which is in fact always 1. And so I could insert here the J of n. And now this is true as n goes to infinity in Q, not just in Z, but with the fixed denominator, or bounded denominator, it's the same. One statement is equivalent to the other. Fixed denominator, fixed fractional part, let's say. Or bounded denominator. It's essentially the same because there are only finitely many fractional parts with a given bound on the denominator. So for instance, if n is some integer, some large integer going to infinity, plus 3/7, then when you expand this thing, even for the original one with 1 over n, when you expand to all orders, you'll get exactly the same power of Cn plus d as before, the same power series, the same e, but the whole thing will be multiplied. For instance, if I took 2/5, it would be multiplied by 46 minus 2 square root of 5. So you get a factor here, which is j of n, which by the periodicity only depends on this fractional part. So as I said, if n is an integer plus 2/5, I would have the previous formula multiplied by that number. So 46 minus 2 square root of 5. So now this does look like modularity because I remind you that a modular function is a function somewhere else in the upper half plane, but it's a function that satisfies this equality just with equality. Notice an asymptotic statement, f of ax plus b over cx plus d is a power of cx plus d times f of x. So this is the modularity, which is still completely open in general. But it's now been proved, well, we proved it in our paper, although now other papers have come out that were faster in writing. We proved it for 1 knot, for 4-1, and Beta and Trapeau proved it for maybe 5 knots. I don't know exactly how many. So there are a few cases where the straight modularity conjecture is actually a theorem. Okay, I have the usual problem. If I erase like this, you can't read it. If I do it the other way, it takes a long time. Okay, so now I have to so now we've got a second invariant, but actually the second invariant is infinitely many invariants. So now to k, I've associated the function j, which is a function from q to q bar. So in other words, j of alpha will be an algebraic number for every alpha. But I've also associated a collection of phi alpha of h, each of which is a formal power series with coefficients. It's a whole business, what field it's in, so on. I'm not going to go into. It's very interesting. So there's a formal power series, and this is for all alpha. So alpha in both cases is in Q, but it's periodic, so it's in Q modulo Z. So now we have 2 invariants. Well, each one is infinitely many. One is a whole function on the rational numbers, and the other is even a double, has 2 indices. It's a whole collection of power series. So these are the invariants that were known. And now the question is, what does one do with them? So before I go on, I want to talk about a strange kind of function. I don't have a good name for it, and if anybody at the end either says such things are known or it's clear you should call it such and such, I'd be very happy. So I'll just call it functions near Q. So functions near the rationals. And it's exactly motivated by what we just saw. Okay, so what I want is that there's going to be a function phi alpha. For my definition, in all the examples, it's algebraic coefficients, but for the definition, it doesn't matter. So it's just a formal power series for each rational number. What you should think of is this: if I have an actual function on the real numbers, and if it's smooth, not analytic, just differentiable, infinitely many times differentiable, then it has a Taylor series at every point, but in particular at every rational point. So that Taylor series may be divergent at every point if the function isn't analytic, but at least there's a formal power series. And so now you forget the function, and you just keep a collection of formal power series. They're completely unrelated. So if I draw a graph, what you would see, well, typically my function will often be periodic, although some won't. Then at 0, you'll see a little graph. But it's not really a graph because the power series diverges. But if I make a picture of a very small neighborhood of 0, it's got a well-defined value, a slope, a derivative, so it's like a little germ of a function. And since the function in my case is periodic, it will be the same here. But then at a half, it'll be some completely other function, which is doing something else. And so at each rational point, there'll be a little piece. It would be like the Taylor expansion around in that small interval, but they have absolutely nothing to do with each other. And the reason I'll come to in a minute, it's that I'm using a topology. It's the discrete topology. Usual topology, there are rational points very close to a half or to any real number, but here they aren't. They're all infinitely far apart. So it's like expanding a function at different points. In fact, if you know modular forms, it's like expanding at the cusps, and that's just what it will be later. So we have a collection of these, and I don't know what to call it. I'm just calling it a function near the rationals, but it's not really a function. But I want to think of it as a function. So you want to think of the following. So it's like a virtual function. We're in a virtual year anyway. I have a variable, which is, think of it as a real number, but it's not a real number. It's a rational number plus infinitesimally small. So I want to be infinitely close to a rational point, alpha. Okay? So alpha, again, is a rational number. But I won't do this in a particular way. So I could just put A over C plus epsilon, but instead I want to take minus epsilon. The signs don't matter, that's conventions, but I want to put epsilon over C. And then the value of my function, the value at this point x, is equal to the power series in this, actually in 2 pi I epsilon. It's the same factor we had before. For this definition, I could drop the 2 pi I since it's in C, but in my examples, I want phi to have algebraic coefficients. So I take phi to have algebraic coefficients that I have to put in the 2 pi I. So this looks a little strange, but we actually see an example, because here, if you look how this looks, an plus b over cn plus t, this is a standard calculation, is exactly a minus epsilon over c, where epsilon is 1 over cn plus d. An easy calculation. And therefore, the argument of this phi alpha is exactly what I call 2 pi I epsilon, and the whole thing hangs together, except that you also have this thing, and I'll allow that in a moment. So this is this weird kind of function of which we're going to have many examples, and one of the 3 invariants I'm talking about is, one of them will be a matrix of ordinary holomorphic functions, but one of them will be a matrix of these weird functions near rationals, of which one entry is the one we've already seen. So first, maybe I'll write that, and then I want to say a little more about. So let me give 2 examples of how such things, or several examples, how such things can occur in nature. So example 1 is C infinity functions, smooth functions. So if I have a smooth function of the real numbers, then it has, so let me write f for these near Q functions. So that just means, remember, a formal power series expansion, not convergent, not anything, at every rational point. So of course, you have maps from C infinity into the space. It's obviously injective, because if you know the power series at every point, you know the value at every point, and it's continuous, so you know the value at every real point also. So we have an injection, so the smooth functions are contained in this funny thing, but in the way that I said. So in other words, to alpha, I associate phi alpha of h is the Taylor series, the nth derivative of n at the rational point over n factorial. But remember, I want 2 pi I n, and so 2 pi I h should be, so what is it, 2 pi I h or h over 2 pi I? It's h over 2 pi I, it's for the n. So this would be my phi alpha of h. So in this way, I associate to a smooth function such a power series at every point. And now you see that Now you might ask, why did I do it in this particular way? Why this A minus epsilon over C? But you already see in the example a little bit, that's what I just explained, the AN plus B over CN plus D, that leads to such an epsilon. But in fact, the point is that SL2Z, or actually any subgroup of SL2R, the subgroup of SL2Z acts on these funny functions because you replace f of x by f of ax plus b over cx plus d. So you just compose with the action of the group. But if x is infinitesimally near a rational number alpha, then of course ax plus b over cx plus d is infinitesimally close to another rational number, which is a alpha plus b over c alpha plus d. But it's not the same h. So I don't want to simply compare phi alpha of h and phi, let's call this matrix gamma, gamma of alpha of the same h. It's some other h prime which you get by this little computation I showed here. It's a 2-minute computation. You have to change variables in a suitable way. So if you think of the function not as a random power series in a fixed variable h, the variable h has a local meaning at every rational point. As I said, h or 2 pi, well, h is 2 pi I epsilon, and the point is a minus epsilon over c. So this is slightly subtle, but still, that's a boring example. But now comes a very interesting thing. This would be elements of the Hadira ring. So that's the next era of my talk. So this was a ring defined, I don't know, 25 years ago, maybe, I don't remember the date, by a very good Japanese mathematician, very famous in particular for this, Hadira, who I think his notation was z of q hat, but I'll just call it h for Hadira. He probably didn't call it that. And so the technical definition is the limit. It's an inverse limit like the p-adics. If this is unfamiliar, it doesn't matter at all. It's just a definition. You take polynomials for each n modular the ideal generated by qn, and qn is the analog of n factorial. It's called the nth Pochhammer symbol, 1 minus q squared, up to 1 minus q to the n. So what does that mean? So a typical function here, a, will be a of q is given, but it's not a unique representation. But you have many representations of the following form. You have a polynomial with coefficients in z, and then you multiply by this qn, but each qn divides the next one. So if you take, the first 10 terms, then all further terms are divisible by q10. And so if you work modulo q sub 10, this series stops and it's just a polynomial. So that's typically, just like you write down p-adic numbers, it's a sum of integers times powers of p in a non-unique way. So it doesn't matter what the technical definition is. It's a wonderful ring, but a function here is a function of a formal variable q. But such a function now has two realizations, and that's somehow going to play the key role, because our three invariants are in some sense three realizations in different worlds of the same matrix of functions, but the functions are being interpreted as completely different objects. So the Hadira ring is a perfect example of this. So, well, first of all, I haven't said what's the function of the rational numbers. So let me call A numerical, or let me just call F. So if A is in the Hadira ring, I'll make A, which is the numerical thing. F of a rational number will simply be A evaluated at 2 pi I alpha. Well, that makes sense, because since alpha is rational, e to the 2 pi alpha, that's the q here, is the root of unity. So eventually, when n is bigger than the order of that alpha, all terms in this series will become 0. So this is a finite sum. And therefore, this will always be an element. That's one of the many beautiful arithmetic properties of the Hadira ring. Its values at rational numbers are always algebraic integers in the cyclotomic field of nth roots of unity, where n is the denominator of alpha. And there are also other arithmetic properties that are very important, but congruences, so that I won't talk about. So this is an example. And now what the point is, if I now think of my x, remember my alpha is going to be a over c, and I put epsilon, then the q should be now e to the 2 pi ix. So that will be the root of unity that we already had, multiplied by e to the minus 2 pi I epsilon over c. So if epsilon is very small, I'm deforming q, but it's infinitesimally. So q is now, let's just call this a root of unity times e to the minus h over c, I want to call it. So h bar would be I epsilon, h over 2 pi. Okay, so that's, but h is, this is a root of unity. Z to some power is 1, but h is infinitesimal. It's very small, so that power series converge. And now you see that that makes sense, because if q is the fifth root of unity, I already said that, then as soon as n is bigger than 5, these terms are 0. But if n is the fifth root of unity and q is the fifth root of unity times e to the minus h, then once n is bigger than 5, that factor is divisible by h. But once I get up to 10, then it's divisible by another h. Anyway, there'll be more and more h's. Sorry, every time that n is a multiple of 5. So if I go far enough, these terms will not be 0, but they will be divisible by h squared, h cubed. And so this gives me a formal power series. And so if I do this, then the original Hadira invariant becomes a power series. Of course, which power series? It depends on the point alpha in h, which is now the same thing as it was before, 2 pi I. H, I guess. I'm going to get all the 2 pi's wrong. So that's a typical example. Now, I haven't actually changed the subject. I'm talking about knot invariance, and it's a theorem of Hadira, a fact that Hadira also proved, that the Jones invariant, which remember J, for any knot, I have this function from Q to Q bar, is in the Hadira ring. And in the case of the 4-1 knot, I wrote the formula in a purposely somewhat non-standard way. Maybe it's still even on the board. Yeah, here it is 1 plus 4 sine squared pi. But you can write this formula as the sum n from 0 to infinity. And now you take the nth Pochhammer symbol, absolute value squared, where q is e to the 2 pi I alpha. Now that doesn't look like a polynomial, but remember that q bar is the same as q inverse. So I could also write this as minus 1 to the n times n plus 1 over 2. Times q to the, minus 1 to the n, and then q to the minus n times n plus 1 over 2. The formula doesn't matter. I'm just showing that the complicated formula I wrote before with these signs can also be written as the sum of terms, each of which is a polynomial in q with integer coefficients. Well, Laurent polynomial, it's the same, times qn. So therefore, in this case, you can see that it's in the Hadira ring, but it's always in the Hadira ring. So our first invariant is one of these funny functions. But we have another one, because remember, I had 2 invariants from the knot. The knot gave me 2 different invariants. It gave me the Hadira function, which I just said is an Hadira ring, but it also gave me a collection of phi alphas. Well, you might think that's the same, but it's not at all. So now let me show that, and then I can get on with what actually happens. I should put this up much higher. Then you probably can't see it, but it's at least out of the way. So, the web thing again. So I have these. It's still not quite good enough. So let me go back to this definition very briefly, because I want to slightly extend it, because our functions will be in the extended thing. So we had this f, where f of x is this power series phi alpha of 2 pi I epsilon, if x is equal to a over c, a rational number. A over c is my rational number. And then I've deformed very slightly, epsilon is infinitesimal, and I've put the denominator c. Okay, so whatever that means, and this is what you should think of, but it's just a collection of formal power series that you should think of as the renormalized Taylor expansions. But now, what we had before in the volume conjecture, we actually had this phi alpha, but if you remember, it was a n plus b over c n plus d in the volume conjecture. This was a over c. And here there was a term e to the v times n plus d over c. That was the exponential growth. Remember, the original volume conjecture was just e to the v times n. But now, the calculation that I think I've erased now, but this is a minus epsilon over n, where epsilon is 1 over cn plus d. So therefore, this thing I can write is e to the power v divided by c epsilon. And v is the volume of my knot. It's fixed. It does not depend on the rational point. So now the more general thing is f hat will contain things like f of x. So v will be a fixed complex number. It is simply e to the power of this fixed complex number divided by epsilon. So again, x is just as here, a over c minus epsilon, times the denominator, which is c, times a power series. So that's a tiny generalization because if v is 0, it's the previous thing. And you could say, well, that's completely pointless because if I fix v, then of course this set is just isomorphic to the other set. You just remove this factor. We're thinking in a different way. But now I want this to be a ring. I allow myself to add finitely many such functions. So you could write it down formally as a tensor product. But anyway, I allow finite sums. So, or more generally, a finite sum, j from 1 to capital J, of e to, and now the v's can be different. So that's what's called formally a trans series. It's a mixture of a power series and exponentials in 1 over epsilon. And as a function, it doesn't seem to make any sense because if epsilon is very small, first of all, this already doesn't converge. But even as an asymptotic series, it's only of the order of 1. So if you multiply different series in epsilon by different exponentials, then the one with the bigger exponential term will completely swamp the other and make it invisible numerically. But first of all, we aren't working numerically, we're working formally. I'm perfectly entitled to write down formal expressions. And secondly, there is a way. Well, there's a standard way called resurgence theory and to Borel transform, but it doesn't work here as far as I know, because we don't know enough about the Laplace transform of these functions, but there is a purely numerical way, given a collection of power series, to make sense of phi of epsilon to much higher precision than you would think. And that precision is such that the error term becomes exponentially small. And so if you do that for all of the series, some of the ones, even with the big exponent, the error term may be exponentially so small that the error is smaller than the next term, and so you suddenly can see the next term. You can't see them necessarily all. Sometimes you can see them all, sometimes some of them, but it does actually make sense numerically, and that was crucial for our experiments because what I'll write down we found experimentally, and we did by actually doing this approximate numerical convergence. So, okay, so now I'm getting there. Finally, I warned you, it's a long story. Maybe I didn't warn you, but I should have warned you. So now we have our third example. Our example here is K is a knot. Phi alpha, there's just one of them for the moment. There'll be more in a second. These are as before. These are the power series before. And so J just goes to 1 for the moment. And V is the volume. So that's exactly what we saw. There was that volume term, e to the V times n plus d over c, which is exactly this V over c epsilon. So now we have two examples. But now is when the story becomes really nice. Because I take now the Kashaith invariant, and remember what the volume conjecture, the modularity conjecture said. It said, actually, I'll put the Cn plus d to the 3abs on the left, as one always does in modular forms, this is the slash operator. The volume conjecture says that this thing is equal to very high precision to, actually, I can even call it phi hat. So let me call phi hat of h to be the formal thing. It's the power series h multiplied by this v over ch, c epsilon, which here, well, because of the h is 2 pi I, it's actually 2 pi I v over h, I think, over ch, where c is the denominator. So if I have a collection of these power series, let me put a hat to mean I include the exponential factors. I don't have to keep writing it. Then the story before was that what you got here was exactly this completed power series, where the epsilon was 1 over Cn plus d. But there was a prefactor, which was j of n itself. Maybe it's safer, n looks too much like an integer. Let me call it x. So it's the same, but it doesn't have to be an integer, and it looks like it's like an integer. So remember, x is going to infinity with a bounded numerator. So this was the original volume conjecture. This was the quantum modularity conjectures. We had it before. But now you can ask, well, if this were truly a modular form, we'd have equality. So therefore, you could say, what happens if I take the left-hand side and I subtract the right-hand side? So I subtract j of x times this power series. Well, it seems to make no sense because the thing blows up exponentially. I gave you a table at the beginning. For n equals 300, the value is 10 to the 45. And this is given by 10 to the 45, that's the big exponential factor, times the power series that is only a polynomial. But as I told you, you can improve the numerical computation of this. And so we can actually subtract this. And so we can ask what happens if I subtract the prediction of cx plus d, and then are there further terms? And that's what's going to lead to the new invariants, because there are further terms. So let's do this for the figure 8, not the original. So I take just the Kashaith invariant, which means 1 over n. So j of n is just 1. This would be phi 0, which is the series I wrote before, 2 pi I over n. Sorry, but it's not, yeah, it's phi 0. And then there will be something. Well, when I compute this for n equals 100, I find that the question mark you can compute to very high precision. I have it written down, but it's something like 1.0014. So remember, this term is something like 10 to the 30. And this is 10 to the 30, but now we've made this so precise that I can subtract and find the difference to high precision, even though I'm subtracting two very large numbers. And what you get is a number which is very close to 1, and as n grows, you find that it's a new power series, which I'll call phi 0. But this time there's no prefactor. Sorry, here, this was just for n as an integer, but if I put j0 of 1 over x, or j of 1 over x, then this will be 2 pi I over x, this will be x. Here, remember, we have the modularity factor, but here, the factor is just 1. It's very strange. There's no multiple. So what you find when you do the experiments is as x goes to infinity, even with the bounded denominator, the thing you subtract is this power series we already had, times j of x, but then there's a new power series without a factor. It's always the same. And I can say what it is. In this case, it's, I remember it by heart, the beginning, it's an even power series because the knot is amphichiral. It starts like this. So suddenly we have a completely different power series. But actually the story goes on because actually there's going to be a third one. So the original one, so remember the phi 0 was the one that I showed you before. Phi 0 of h started, I won't write the whole thing, but it started h over 72 square root of minus 3, and so on. So they put coefficients in q square root of minus 3. But phi 0 has coefficients, so this is phi 1, the original phi. This is a new one, still at 0. We're actually going to have this at every alpha. So now if I do it at every alpha, then there will be a second power series, again, depending on alpha, but now it's a new one, it's the 0th one. You'll see why in a second, same argument. And that's always multiplied by 1. But now we can do the same thing again. As I said, this numerical procedure is so good that even though this term might be 10 to the 30, and this is also 10 to the 30, but when you subtract, this is of the order of 1, you can see it. But you can even subtract it, now it's of the order of 10 to the minus 30. And if you're lucky, you can see the next term. And it turns out, in this case, that there's a new function, q of x, stupid notation, no, not q, j star of x, we used to call it q. And then there's a third power series. So this one turns out to be 1, this turns out to be 2, this turns out to be 0. But now it stops. No matter what you do and to what precision and what other knots you look at, there are only finitely many terms. And each term, so it's a finite sum, and now you see that's exactly like what I described here. We have a finite sum of things which at each point is a fixed sum of a finite size. This is the J and the VJs are independent of alpha, but the power series depend. So we have a collection of power series, and now we have three such collections, phi 0, phi 1, and phi 2. So let me write that a little better. I told you there was going to be a matrix invariant. I now write it down. Okay, so I'm now going to associate to my knot phi, but I'll now I'll underline it twice to mean matrix, since I don't have other fonts at the board. And this will be a collection of phi alpha of H, so power series, but actually I want it to be completed. And remember, each of these things will be V alpha divided by whatever it was, 2 pi I over C times H times the power series. So I have a collection, I mean, forget all these 2 pi's and so on. They're completed power series, so they have these exponentially terms, some that were exponentially big, some are exponentially small, but we have a collection of these V alphas, sorry, the V is not V alpha, the V is Vj, which I didn't tell you, Vj, J goes from 0 to R, remember R was the rank, V0 for the triple connection is just 0. There is no volume. For the geometric connection, it's the volume of the knot. And for the next one, it's the one well, it was called little v, so it was V over 2 pi. And for the anti-geometric, it's minus V complex conjugate and so on. Anyway, they're numbers that you can compute in terms of the dilogarithm. These are computable numbers. So we get a collection of formal power series. And now this matrix, how will it look? I'll just draw it for the figure 8 knot. So for the 4-1 knot. So phi alpha of x, well, I'll just do it at 0, but with the hat. So I already told you it's r plus 1 by r plus 1. R here is 2. Remember, we have the quadratic field cubed squared of minus 3. Then here, I have this new power series, phi 0. Well, phi 0, 0 if you want. And here I have phi 1. And here, as it happens, because the knob is amphichiral in general, these series are all disjoint, but it happens that phi 2 in this particular case is simply phi 1 of minus h, and when I put the hat, it's still true. This one doesn't need a hat because the volume is 0. So I've actually written down what these things are. Phi 0 at 0 is the one that's up there, so it was the one that starts 1 minus h squared plus 47/12 h to the 4th, so it's an explicit power series. This one started 1 over the 4th root of 3. I hope I didn't forget it, plus 11 times whatever. I've written it twice. And the next one is the same. And then there'll be 2 more that I'm not going to write, but they're just as explicit, that we find by continuing this expansion to the next level. I could explain it in 3 minutes, but time is getting short, and I'll skip that. So if you remember how we got this column of numbers, we got it by this numerical procedure. But that's actually not true. We already knew those series before, because I told you what phi 0 was, but I didn't tell you it was phi 0. I told you that the Jones polynomial here, I told you that this Kashaith invariant generalized, so the Jones version of it, is a function which is in the Hadira ring. I said that, it's in the Hadira ring. And that means that I can expand it, not just its value at rational points, but there's a whole power series. And so in particular, I can expand at alpha, like at 0. So if I do it at 0, I'll take this infinite sum that we had before. Well, I'm not going to write it again, the qn squared, it's on some earlier board. And when I do that, if I take q equals e to the h, where h is infinitesimal, so it's not even a small number, it's infinitesimal. So powers of it converge, so to speak, by definition. If you take q equals e to the h in the formula that was on an earlier board a minute ago, in the Hadira ring, you will find that here j of, the original a of e to the h will become exactly 1 minus h squared plus 47/12 h to the 4th, and so on. So in other words, in these two invariants, which are always in this position, one is in the top position of the first row, except the first column is always 1, 0, 0. But the first non-trivial comment, the top one is the element, the Kashaith invariant, as an element of the Hadira ring that expanded formally around alpha in the way that I just explained at 0. You take your Q to be the root of unity times e to the minus h, and you expand and you get a power series. That's this power series. But this one is not at all that. This is the one that comes from the quantum modularity. It's the leading term in this asymptotics. But now, in the case that I told you for the 4-1 knot, remember phi 1 was 4th root of 3, which is really the square root of minus 3 up to root of unity. And then it was 1 plus 11h over 72 square root of minus 3. Then phi 2, I told you you send h to minus h, but that's a coincidence. What you really do, it's the Galois conjugate. And the conjugate of square root of minus 3 is, of course, minus square root of minus 3. So in general, if I take another knot, I'll have many of these series, but each one has coefficients in a number field. And remember, the first group of number fields were all conjugate. You just conjugate the coefficients. So we actually knew, remember for the knot K3, we had 0, and then we had 1, 2, and 3, which performed one orbit, one Galois orbit, and then we had 4, 5, and 6. So now I've explained this series. It comes from the Hadira ring element expanded around 0. This one comes from the modularity conjecture. These come by conjugating the first one, and then these you need a new recipe, but that was done 3 or 4 years ago in a paper by Dimofta and Garoufalidis. I won't write it out again. So they found a natural way to produce a collection of power series canonically indexed by the flat connections, such that the first one numerically agreed with the one I'd found in the quantum modularity conjecture in all cases. So these power series were already there. But what is new in this story, well, besides the fact that it's true, if you look at that formula at the top, this thing, as you expand, remember, we first had the modularity conjecture, then we subtracted, got something new, a new power series. But it wasn't new because actually we knew phi 0. And the coefficient was boring, it was just 1. But the next coefficient was a power series we knew, it's the conjugate of this one, but there's a new function, j star of x, which turns out when you make a table of it, again, to have Hadira-like properties. And in fact, it's again, so I told you that Hadira proved that the Kashaith invariant is in the Hadira ring, but the second invariant also is. And if I do not with higher rank than 3, then here it would go from 0 to 3. So I would have phi alpha j, j going from 0 to r, which is the rank, and then each phi alpha j times an element of the Hadira ring. So that produces a bunch of elements in the Hadira ring. And so that gives me my next matrix valued invariant. So this was one invariant, but the next is a Hadira invariant, j of alpha, which will be, well, I'm not going to give the whole thing, but it will start j of alpha here, the original j, this is underlined to make it a matrix, and here what I call j star of alpha. And here there's some new ones which I'm not going to go into. They don't have algebraic values, but they nearly do. The values of these, remember, the Hadira, this is the Hadira ring, so its value at any rational point is an algebraic number in a cyclotomic field. These other numbers are nearly algebraic, they're algebraic multiplied by e to a multiple of the volume, so it's practically. And they turn out to have beautiful things, and it's a generalization of the Hadira ring from something based on Q to something based on number fields, but it's much, much more subtle. That's work in progress with Garoufalidis again and Peter Schulze. So there are higher Hadira rings with extremely subtle, much, much more subtle than the original one, number theoretical properties, and the further rows of this new invariant turn out to be in that. But I haven't said where they come from, because so far the thing I wrote only involved the first row. But that's because I was expanding the original Kashaith invariant. But remember, the original Kashaith invariant was this one, but its constant terms are this j. So what I can do is I can take the other phis, of which are indexed by number alpha, but also by an index from 1 to r, and I can take their constant terms, and those are periodic functions, and those are the generalized Kashaith invariants. And so I get a function here, so I get a generalized thing. Okay, this is getting very abstract, and now I want to come to something much simpler and really pretty, and then I'll slowly be coming to the end of my talk. I was told it can be a little more than an hour. So, So we have these new invariants, each of which is a matrix. One of them is a matrix of these functions near rational numbers, of which there are many other examples. For instance, modular forms, mock modular forms also give such functions near the rash. I don't have time to go into that. So we have one of these functions, which are these Hadira-like functions that I called J, this matrix of J's. So I've associated to my knot, first of all, a collection of phi alpha hat of x. So this is a matrix. It's an R by 1 by, actually it's invertible. The determinant is in fact more or less 1. So it's SL R plus 1. It always has block form, as I mentioned. So it's R plus 1. It looks like that. And here I have these functions, well, the extended functions near rationals. Remember, those were things near Q. So these were the things that near every point, A minus epsilon over C gave me E to the V some volume over C epsilon times the power series in 2 pi I epsilon. So that's one of the invariants, takes values, it's a matrix, but the elements of the matrix are these strange functions defined almost everywhere. And the other one is just a periodic function, it's essentially the Hadira. So the other is J alpha. So alpha is always a rational point and it's periodic. J alpha is simply a matrix of complex numbers, well, algebraic, essentially algebraic numbers. But now comes the amazing thing. So let me take the K1 node again. It's a 3 by 3 matrix, but I'm not going to worry about the top. Let me concentrate on this 2 by 2 part. Okay? So that's the sort of interesting part. If I draw it, so I make a graph. Here's X. Of course, X is just rational numbers. So what I get, I have to draw all the rational points with the denominator that's up to 20. Between 0 and 1, it's periodic. And when I do that, and we have the graph in the paper, you just see a cloud of points. It's a complete mess, as you'd expect. So this would be the graph. This is alpha, which is in Q. And this is the graph, J of alpha, which is, remember, a matrix. So there are actually 4 of these clouds. But when you on the screen, when you superpose 4 clouds, you just see 1 cloud, a little blacker. But now comes the amazing thing. Now we look at the modularity. If I look at, so here, X, but I only have the rational points. If I take minus 1 over X, because these are matrices of determinant 1, I can invert them. So I can now invert the matrix J of X and multiply on the left by J of minus 1 over X. And then I can draw the 4 things. And now when you do it, what you find, and we can even prove it in this case, you find 4 smooth curves. So this thing, these are matrices which are just, this is alpha is in the rationals. So this is a matrix valued function which is jumping all over the place. But this thing is suddenly a 3 by 3 in this case, R plus 1 by R plus 1. Well, I'm just taking the bottom part. It's an R by 1 matrix, but now it's in C infinity of R. Well, it's not quite, but it's R minus 0. It's not quite C infinity. You can do it to the left, but there's a problem at 0. So you get something absolutely amazing. You start with invariants which are only defined at rational numbers, and they're jumping all over the place. But it's a matrix, and a matrix can be inverted because it's here non-zero determinant. And now when you take the cosine, so more generally, well, actually it follows more or less from this. If I define J, if X is originally a rational number, and gamma, as usual, is an element A, B, C, D of SL2Z, then I define W gamma of X to be J of X inverse times J of gamma X, which is usually X plus B over Cx plus D. Now it's a small x, I mean, x isn't going to infinity, but this function now, that's the amazing thing, is suddenly a C infinity function on R. Actually, there's always 1 point missing, which is minus D over C. It's a slight problem here. So you get it's suddenly this function which was only defined, this was originally defined, J is, this was the matrix, I'm not going to keep putting the lines. So J was only defined for rational numbers. But now when you graph it, it's continuous, so you can take the closure and you get a function on R, and it's not just continuous, it's smooth, actually it's even better. It's actually real analytic. And we know that. Well, we can't prove it in all cases, we can prove it sometimes. So that is the new invariant. And now if you know the notion of cohomology, you'll see that this W gamma, because it factors in this way, so this is J of X inverse times J of gamma X, That's what's called a co-boundary, and every co-boundary is a co-cycle, which means I'll get it wrong with left and right, but roughly it says it's just a trivial consequence. Either like this or it's the other way around, that there's a formula relating W with index gamma times gamma prime to the formulas for gamma and gamma prime. That's called a co-cycle. But this co-cycle, if it were a co-boundary, if it had the form J of X inverse times J of gamma X, it would be a boring co-cycle. You can do that for any function. But it's not, because W gamma is in the space of analytic functions. And there it doesn't factor like this at all. So you get a non-trivial element of H1 of SL2Z. With coefficients, it's here, it would be SL2 of C infinity. Well, C omega star of R, which means functions that are analytic except for finitely many breakpoints where they don't have to be analytic. So SL2Z acts on that space. So it's a very weird cohomology group, but that's where our final invariant lies. Okay, now I still want to take a very small number of minutes since I was told I can go on a little more than an hour. And there was the introduction, so I think I'm only barely over the hour. I want to say very, very briefly the final story. I told you that we defined 3 invariants. And this story, how we found the third is very amusing, but I won't have time to tell it. It was by sheer coincidence, by just serendipity. We were looking at something else and found a function and happened to notice that certain numerical invariants coincided with the ones coming from the 4-1 note, which we knew by heart. And after 10 years of investigation, it all turned into a theory. But we have a third invariant. So I already have this matrix of Hadira-like functions, so in this near rationals. Then I had the phi hat, the phi hat thing. But the third invariant is now suddenly going to be a holomorphic function, Q of tau. It will be an invertible matrix, again, this block form. In holomorphic functions, well, to simplify, I'll just say the upper half plane. It's actually the upper and the lower half plane. So off the real line. So I want to get the definition. Well, we don't even have a definition in general. We have an explanation how to find it for any knot, but we don't have a guarantee that that method will give something, but it always does in practice. So if K is my 4-1 knot, my first example, then this thing looks like this. It always starts 1, 0, 0. The top column I'm going to drop. We didn't find it, and it was found by a doctoral student, Campbell Wheeler. Well, he didn't find the series, but he made a suggestion that worked, maybe even found it. But here, these were the functions we'd found by chance. There's some functions, G0 of tau, G1 of tau. And let's call it G0 star of tau, G1 star of tau. But all of these are Q series, they're periodic. So they're power series, as in modular forms, in the variable e to the 2 pi I tau. And I can write down what they are. G0 is the sum minus 1 to the n, q to the power n times n plus 1 over 2, divided, so this is what's called the NAM sum, or a Q hypergeometric series, by qn squared. And if you remember the form of the Kashaith invariant, which you probably don't, it was minus 1 to the n times q to the minus n times n plus 1 over 2 times qn squared in the numerator. So it was kind of the, Stavros calls it upside down cake. So you turn it upside down, but this is a perfectly well-defined series. I forget how it starts. I have all the coefficients written down. And then G1, you write down exactly the same thing, but you insert a factor 6n plus 1. So that starts 1 minus 7q. And G0 star, G1 star, you write down something else. So they're explicit series. I could give you all the coefficients you want. And this matrix, the determinant of this matrix, is elementary here. It's q plus 1 over q. So each of these functions is completely transcendental. Okay? But the whole function, of course, is holomorphic. And so you see that actually it's even more. It's holomorphic functions of T. T is the translation, corresponds to the matrix 1, 1, 0, 1. That means that these are functions such that q of tau plus 1 equals q of tau, which means it's a power series in little q. So this is a completely different invariant. These are now holomorphic functions. But now I can come to the most beautiful part of the whole story for me, because it's a new kind of function that I hadn't seen. If you've had a course on modular forms, you've seen a picture where the topology of the upper half plane, you have to go to the boundary. The cusps are all rational points, and you make a little disk of a certain radius at each point each rational point, and these disks are disjoint. So that's just what I was saying before. At every rational number, you have an infinitesimal neighborhood, but they don't overlap. But in the real line, that seems very strange, because no matter how small the neighborhood of the third is, it will contain rational numbers. But these little neighborhoods are truly disjoint. And so imagine that you have a holomorphic function here, which is periodic, but as you approach a rational point vertically, or it doesn't have to be vertically at any angle in this disk, it will have an asymptotic expansion in epsilon, where epsilon is the distance to that point. Exactly the way we did before. You write the point as a minus epsilon over c, but epsilon is now this negative imaginary part. And when you do that, then you'll find that our particular functions, this has an expansion, has asymptotic expansions, but there is also a volume term, expansions at every rational point. So at every rational point, if you're at the distance epsilon, the way before a minus epsilon over c, then you will get a power series in epsilon multiplied by e to some constant over epsilon. But you'll have a finite sum of those. You'll have a finite sum of those series. And guess what? It's the same power series as the ones we had before. So the asymptotics of these forms, these asymptotics, so each q, in this matrix, each qij of tau will be asymptotically to all orders a finite combination of these phi hats. So it's combination of the same power series. Now I come to this Q series. And now the very last thing, and then the lecture is over, is this. These functions are not modular, of course. But even if they were a modular function is defined in the upper half plane, but it never extends across the real line. So this function, which is even less than modular, of course, Q of tau is in the it's holomorphic in the upper half plane, or if you want the upper and lower half plane, so C minus R, but definitely not across the real axis. There's no part of the real axis that it can ever extend across holomorphically. It's a periodic function. But now we do exactly what we did before. I make a W gamma of tau, but now the holomorphic version. So this thing, I do exactly what I did before with the J function, but now I take this matrix of holomorphic functions. Sorry, inverse. So gamma again is an SL2Z. And so this thing by definition is holomorphic in C minus R. But now comes the miracle, and this you can prove using the so-called state integrals of Kashaev and others. You can prove that this function extends holomorphically to what I call C gamma prime, which means let's say that the matrix, just to fix things, C is positive, otherwise you reflect the picture. Then you take the point minus d over C, which goes to infinity. You cut from there to minus infinity. And then you take the whole cut plane. So it's the upper and the lower half plane plus the axis to the right of minus d over C. So it's an amazing fact that this thing extends. However, it also extends this function, but does not extend to the left. But you cannot distinguish between gamma and minus gamma, because minus A, minus B, minus C, minus D is the same gamma of tau. So if you do it the other way, there's an automorphic factor I can't explain. So this actually not Q slash gamma, it's Q slash in some weight. There's some weights. And the weights will change if you change gamma to gamma inverse. Then you get a different thing which extends to the other side. So now if you take this first extension, forget the complex numbers and just restrict to the axis to the right at this point and take the other minus gamma to get to the left, then this will give you a W gamma, which is again a matrix valued function with coefficients now in C omega of R minus D over C. So we again get a cocycle. And now the final statement of the whole story, these two cocycles agree. So we have two wildly different invariants, but we feel that they're manifestations of the same function, which is one of these strange functions near rational points with the holomorphic version, rational version. We have two completely different functions. One is a holomorphic function, periodic in the upper and lower half planes. One is a function which is not even a function, but a collection of power series around rational points on the real axis. Each time when you make the co-boundary Q of tau inverse times Q of gamma tau, or J of tau inverse times J of gamma tau, you get, of course, a cocycle, but that cocycle suddenly extends to the real axis. Either it extends holomorphically from above the real axis and below to the real axis, or it extends continuously from the rationals to the reals. And so you get two cocycles, and the final story is that the holomorphic one is equal to the Hadira one, or the perturbative one. So we get these invariants which are linked. And so the final step is just a single cocycler, but two different places where it becomes a co-boundary. Okay, I'm sorry, it's a very, very complicated story, but I hope that something emerged, which is the excitement of seeing that just starting with the numerical properties of invariance of a knot, which seems to have nothing, it's just something you draw with a piece of string, that you first get volumes, then you get algebraic numbers, then you get power series, then you get asymptotic statements, you get the modular group acting. The story keeps going, but it finally closes up, and there aren't, as far as we know, any more invariants. We've been studying it now for 10 years. This seems to be, it closes, and this collection of invariants is self-contained, and the final statement is this one. So I'm sorry that that became difficult and also a bit long, but an hour and a quarter, I was told, is all right. So I'm finished, thank you.
I'm not sure how shall we thank the speaker by Zoom?
Well, that's kind of pointless, but if there are questions, that's of course much more interesting.
Right. I don't know, are we going to ask for questions in the chat?
Yeah. Why not?
If people can post their questions in the Q&A box, that would be.
Well, if there are people who can speak because they're connected, then of course they can speak, but otherwise it will have to be by chat, I guess.
Well, I can repeat the questions, but.
Well, obviously, otherwise I wouldn't see it. So you better repeat it. I don't have the chat.
Did I see? Yeah, I don't know if we can allow, that's a question for Ryan, if we can allow people to ask questions directly.
Well, in the meantime, you can ask a question if you have one, since you're connected, while people are figuring out which button to press.
So my only question was to get, is there any sense like which modular forms these are? I mean, I guess that they're not.
Well, these aren't modular, yes, of course, they aren't modular forms in any sense at all. So when I talked about these functions defined near roots of unity, near rational points, one example would be a true modular form, let's say a modular function to keep it easy, but that's a very stupid example because, hey, take the J function or a modular function of some level. Then at each rational point, there'll be a power of Q tilde, which is the Q at the other cusp. And then to all orders, because it's a power series in Q tilde, so the volume term, the E to the V, will depend on the cusp. So there are finitely many classes, finitely many Vs. But the power series will just be a constant power series at each cusp, which is the constant term of that expansion. But if you take a mock modular form, it's also holomorphic in the upper half plane. Sorry, do I? Yeah, if I take a mock modular form and go towards a rational point, then it will have exactly the behavior I told. There will be a power of e to the 1 over epsilon multiplied by an entire power series. That's the new phenomenon for mock modular forms that ordinary modular forms don't have. So mock modular forms give that property, and they also have a property that if you make the same difference, the form minus the form at gamma tau, it's not zero, but it extends across part of the real line. So in that sense, there's something in common at these functions with at these mock modular forms. But these functions are not modular at all in the sense that there's no relation directly between the value of the function at tau and gamma tau. The relation is very subtle. Those numbers are independent. When you subtract one from the other, the function you get suddenly extends across a part of the real axis, or if you do it correctly, across all parts of the real axis. So you get a function, you get a cohomology class in a very non-obvious way. So it's a phenomenon you wouldn't see for ordinary modular forms. You would always get the trivial cohomology class. But here we're getting non-trivial ones.
Thank you. So I have one question, which is, does the Alexander polynomial fit into this framework?
Sorry, I didn't catch it. Can you either show me or speak more clearly?
Does the Alexander polynomial fit into this framework?
Oh, well, the answer to that is I'm not a topologist. Although I've seen the Alexander polynomial, I actually can't remember. I more or less remember the definition. There is a link between the Alexander polynomial and Jones polynomials. And there's definitely a link between Jones polynomials and these. But no, so far as I know, it's not. I think the Alexander polynomial is weaker than the Jones polynomials, but I'm not even sure. I'm not a topologist at all. I'm a number theorist. So it certainly doesn't not enter our story at all, so far as I know. Although Garoufalidis probably would say there is a connection, but I don't know it. So it's a good question, but a bad answer.
There are quite, hold on. So there's another question is, does Grothendieck's theory of descent relate to what you've done? Both produce an algebraic number field from a floppy object.
Well, but that's not new. I mean, the trace field of a hyperbolic knot has been known for 40 years. That was just the introduction. I said that knots intrinsically contain number theory. There's an underlying number field. Actually, these invariants have extremely subtle properties. Already the constant term of the invariant, so where these power series that I talked about lie, remember one of them had a fourth root of 3. But if that was at 0, if you look at other rational numbers, you find that the power series is the product of a unit times a power series with coefficients in the trace field. But that unit is an extremely subtle unit that we wrote a paper again with Garoufalidis and Caligari about 3 years ago, and that unit depends on the class in K theory. Here, the class in K theory comes from the knot, but you can make the unit without having a knot. From any class in K3 of the field, you make a certain unit. And so far as I know, that was a completely new construction of units in number fields, or in cyclotomic extensions of number fields. So that was a very non-obvious piece of number theory that in the end doesn't mention knots at all, except that this is a nice example. Because those examples, you just start with a number field, an element in K3 of the number field, and from that you construct a collection of units. But if you have a knot, then if you take the number field to be the trace field of that knot, and the element in the block group to be the element associated to the knot, the fundamental class, then what you get is the constant term of this power series. So these power series led to a new construction in algebraic K theory. So there's actually quite non-trivial number theory going on that I suppressed in today's talk. I mean, everything could have been complex for all the difference it really made today. But it's very much a story about algebraic numbers.
So another question is, there's a way to define Kashaith invariant for one tetrahedron as a 6J symbol and studies asymptotics. Does there exist a version of this story for one tetrahedron?
I think the answer to that, so there's a thing that I'm sure you've heard of or know, probably better than me, called the 3D index, which is due to Dimofto, Gaiotto, and Gukov, I think, if I get it right. And the 3D index is a Q series, which is produced. You can write it down for a single tetrahedron, and then with the gluing of the tetrahedron, it's like gluing data, the so-called Norman-Zagier equations, actually, which tell you how to get this number field and everything. You can glue those pieces together to get the 3D index, but there is a piece for each separate tetrahedron for that. And that 3D index, I didn't mention it today, but for instance, for the case of the 4-1 knot, I had two power series, G0 and G1. And when we found them, we discovered, and now it's been proved, I think by Gaiotto, I've forgotten who proved it, that the product of this power series, G0, which begins 1 minus Q, and this one, which begins 1 minus 7Q, so the product starts 1 minus 8Q, that is exactly the 3D index. And the 3D index is made up one tetrahedron at a time. And actually, the asymptotics of this, the way the power series come, is by the gluing equation of the tetrahedra. So it's very intimately related with the gluing structure if you have a triangulation, say an ideal triangulation, but that's a very long story. But that's where, in particular, the power series, I mentioned that these power series, phi 1 came from my conjecture, but phi 2, phi 3, sometimes it was just the conjugates, but they were new ones. And I mentioned that was work of Dimofte and Garoufalidis. And for that, they used exactly the gluing of the tetrahedra, and you do something with the steepest descent. You write down a kind of a state integral, and you analyze its asymptotics in H, the way you always do, and you get an expansion, and that is how these series come. So it absolutely comes from the gluing of tetrahedra. It does come from a triangulation of the three manifold.
And there's one more question, which is, can we say something about the derivation of this type of modular form? Maybe it means the derivative.
I don't know what you mean. First of all, I don't know what you mean by the derivation, or whoever is asking. Does that mean the derivative, or does it mean where it came from? Derivation has two very different meanings.
I don't know. The question is derivation.
I mean, these are collections, as I said, they aren't modular forms in any sense at all. What they are is they're functions which have no modularity properties. A Q of tau is not related to Q of gamma tau, but when you divide one by the other, then you get something which extends. So this is what I now call a holomorphic quantum modular form.
Yes, the question was about the derivative, apparently.
What? Well, the derivative
is about the derivative.
Well, the derivative is built in because these functions were collections of power series. A power series is a formal power series, sum a n h to the n. Of course, it is a derivative, it's just the sum n a n h to the n minus 1. So, of course, these things are C infinity. They are infinitely differentiable, but they're not C infinity on R. They're C infinity only on the rational numbers. That was the whole point of these functions. You have a power series expansion, like a Taylor expansion, at all rational points. So, of course, you can differentiate it. You just shift all the indices by 1 and change the n factorial to n minus 1 factorial. So, of course, these things, that ring indeed has an operation, which is derivation. And the Hadira ring, that's well known, the derivative of a function, the Hadira ring, is also in the Hadira ring. So, indeed, this whole space, it's not just a ring, it's a differentiable ring, but it's very, very far from modular forms. I mean, modular forms, we give kind of trivial elements in it, which are.
Okay.
I think we're running out.
I think we're at the end of the time and also of the questions. So,
thanks a lot, Don. That's a beautiful talk.
Well, it's not a beautiful talk, but it is a beautiful subject. That I can guarantee.
Both, yeah. Okay, thank you very much, Don.
thank you.
Thank you also. Thank you all for organizing and for having me.
Yeah. Okay, bye.
Bye.